Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel, and in today's video, as you can see the heading, we are going to study and we are going to understand here the L'Hopital's rule for the indeterminate forms. Now you might be thinking what she's talking about, what kind of indeterminate forms she's just going over through. So you see, last time I just tried to make you clear the epsilon-delta rule of the limit. So we were just discussing limits in the last video. You can see its link in the description box. So this video is also connected with the limits. Okay, like for instance, I just say that I'm having two functions, f of x and g of x, for instance. They are very well defined. I'm just writing them in general. I'm having two functions, f of x and g of x, and I just write these two functions in a quotient form, okay, or in a form of a fraction. And then I just going to I will be applying here limit x is tending to some real value. It could be finite, it could be infinite, no matter what it is a real number, okay? So, and over here f of x and g of x are adjusted in a form of a quotient, okay? So they both are collectively forming a rational function altogether, okay? So once when I'm going to apply limit on this entire quotient of functions, the limit is going to be applied individually on the numerator function as well as on the denominator function, okay? And those who have studied limit already at the primary level, so they know how to apply the limits on a function. It's quite well understood. So we individually apply the limit value on these two functions. So after applying the limit value on these two function expressions, if we are having value 0 in the numerator as well as in the denominator, or we could have value infinity upon infinity after applying the limit, okay? Or sometimes we could have some other indeterminate forms. So you see, these forms are not natural, they're not normal, right? So we call such kind of forms as indeterminate forms, okay? They're not naturally occurring. So how to avoid having such kind of situation after applying the limit to functions which are expressed in quotient form? So in order to avoid or in order to get rid from such kind of situation, we apply a rule here, L'Hopital's rule, which was introduced by a French mathematician. His name was quite typical here. It's said to be Guillaume de L'Hospital, so that's what his name was. So his period was actually from 1661 to 1704 80. Okay, he basically belonged to this period. So he introduced a method in which he dealt such kind of indeterminate form, and he just sorted them out in quite logical way. So how we are going to apply this rule, what is the methodology, that's what we are going to study, we are going to understand in this video. And over here along with these two indeterminate forms, 0 upon 0 and infinity upon infinity, we are having some other indeterminate types as well, or indeterminate forms as well. So what are they? They are like, after applying the limits, you can have a situation like this: infinity minus infinity. My infinities are too bad. And we can have 0 power infinity, 1 power infinity, right? Or we could also have positive infinity upon negative infinity, or we could have negative infinity upon positive infinity, such kind of situations. So how to get rid from such kind of indeterminate forms? L'Hopital rule is going to help us here. That's what we are going to understand in this video. So in this video, I am just going to discuss here this 0 upon 0 indeterminate form, and we are going to discuss here an example through which we can better we would be able to understand the concept, how to handle such kind of form. So what we do here, we keep on applying the limit, we keep on checking. As long as we are having indeterminate form, we keep on differentiating the numerator function and the denominator function, then we keep on applying the limits, we keep on checking if the indeterminate form is persisting, we keep on derivating till finally we get some nice distinct finite value after applying the limit. Okay, so that's what the strategy is. So let's go over through and try to understand an example here. I have selected here a very nice example. I hope you are also going to enjoy it. So let's go over through it. And one thing more, that in this video I'm discussing just this form. In the next coming videos, inshallah, we are going to discuss these remaining other forms with the relevant examples. Okay, so here we go, the example. Okay folks, so here this is an example that we have to evaluate. Okay, that's what we have to evaluate here. This is entirely full function expressed in quotient form. So I just take this function as my f of x and I take this function as my g of x. All right, so and individually I'm going to apply the limit on this numerator function as well as the denominator function. You see here, if I'm talking about this log, this is log of base e here, it's understood. We are going to take this log as a log of base e because you can see here that in the numerator we are having e. So in order to handle this Euler number, we just assume that let this log is the log of base e. Okay, so it's like that. So you can also replace log of base e by your ln notation or natural log notation. You can replace it like this as well. Okay, so I just say that this is my natural log, and is going to be written like this. Fine. Now I can apply my log characteristic, that if at the at this position, if you're having any value expressed in quotient form, you can apply the log basic characteristic, which is like, if my log is, I'm sorry, this page is too much bothering me. I better put some weight here. Just hang on for a second. Okay, so you can see that if you're having a log, no matter of which base you're talking about, if you're having a quotient value at this position, then it is going to be expressed as ln of a minus ln of b. So we are going to use this property of log over here. Okay, so actually we are going to take the help of all kind of mathematical tools as much as possible. So that's it. So it is going to be log of this polynomial, or log of this numerator, minus log of this denominator, upon tan of x minus x. Now you can use your scientific calculator. You know that ln of e is 1. Okay, so at this place you can write 1. You can observe here that yet I haven't applied limit. Okay, so I'm just working algebraically here till now. This is it. Now you see, if you apply limit over here in numerator as well as denominator, at the place of your x, once when you apply 0 here, if you apply limit, are you getting a unique definite answer, or are you having an indeterminate form? So let's check. And before applying the limit, I just enclose this step just to highlight it, that what we are going to do now. Now if I apply a limit here, if I apply my limit here, what is going to happen? I can do my work here. Sorry, it's a watch guard whistle outside. Okay, so once when I apply my limit, what is happening? At the place of my x, I put 0 all over around. Okay, so you see, no matter what base you're having, if you're having power 0, it becomes 1. So that's it. So you see, it's 1 plus ln of 1, which is going to be 0, minus 1 upon tangent of, I forgot to write 0 here at these positions, sorry for that. So tangent of 0 is 0 minus 0. So you see, it's ln of 1 is 0 upon 0. You are having indeterminate form if you apply limit at this position. Okay, so what to do? We apply L'Hopital rule now. Now comes the tool of L'Hopital, that we are going to differentiate the numerator and the denominator one after another. Okay, so let us differentiate these functions. Let's see what we get. So I just preserve my limit right now. Just take it in a sense that you haven't applied limit yet. This work is something that you did in your mind, and you come to know that this is an indeterminate form after applying the limit. So you haven't applied limit right now. You apply the rule of L'Hopital, and you see that you are going to differentiate your numerator. And you're going to differentiate your denominator. That's what the rule says. Okay, so you are well aware with the derivatives of these functions, so we are going to apply it as swiftly as we can. So the derivative of e of x, e power x, is e power x, and on the chain rule you're having 1 back, so that's it. Derivative of ln of 1 minus x is 1 upon 1 minus x. Yeah, and then you apply chain rule on this 1 minus x, minus derivative of 1 is 0. Okay, derivative of tangent x is secant square x, minus derivative of x is 1. Okay, so once when you take the derivative of this 1, it becomes 0. Derivative of minus x is minus 1. All right, so that's what we get. Upon secant square minus 1 is your tangent square, because we know that 1 plus your trigonometric rules and trigonometric relationships, if you remember, you know that this thing 1 plus tan square x is your secant square x. So this thing reveals that secant square x minus 1 is your tan square x. So we are going to replace secant square x minus 1 by a tan square x. We're just trying to make our function as simple as possible. Now in the numerator, I can take my LCM thing, right? So try to simplify your quotient functions as much as you can, and after that you just prefer to apply your limit. Okay, so that's what the strategy is. Minus 1 upon this thing, and this thing is actually getting divided with your tan square x, so it is getting multiplied with the reciprocal of your tan square x, right? So that's it. Sorry, it's limit x approaching to 0. Okay, I hope it's clear up till now. Now what to do? Don't apply the limit right now. Let us do some nice adjustment. One more little adjustment. If I divide and multiply by my x squared, okay, and then I again take the limit, and I can write this x squared with my 1 minus x. X squared, this x squared upon tan square x is going to be adjusted like this. Okay, now what to do? You're going to apply the limit over here and here. Okay, you see this is the product of two functions, and both functions are in quotient form. So whenever you apply limit on the product of two functions, you apply the limit individually on this function and on this function, right? So that's what we are going to do here. And I can write here x squared minus x cubed, and then the limit x tends to 0, x upon 10x. You see both these functions are in whole square, so you can just write are having squares on them, so you just write them as a whole square. So it's done. Okay, now we are going to apply the limit here. What is going to happen right after that? So you see, now what we do, we are going to apply L'Hopital rule individually on this function and on this function, because if we apply the limit here, I can see that still the indeterminate form exists here. You see, if I roughly do the work, before doing the work roughly, before applying the limit roughly, I just enclose this step in a nice box. So once when I apply my limit here, you see the indeterminate form exists. Wherever I'm having my x, I just put my 0 there. Okay, so it's gonna be 1 minus 1. You see, it becomes 1 minus 1 upon 0 minus 0, so it is 0 upon 0. So you see this thing, the indeterminate form is still here, it exists. And if I apply my limit on this function, you see 0 upon tangent 0, so it is still 0 upon 0. Okay, so you see indeterminate form is still existing, so we just apply derivative over here and here, here and here, and then we once again apply the limit. So let's see. So I'm going to differentiate my function. This ex minus x into e power x minus 1, and I'm differentiating my denominator, and I am differentiating inside this whole square. I'm performing the activity. I'm going to differentiate my numerator as well as my denominator. Just don't go on my writing, just go over through the concept. That's it. My writing is too horrible. So you see here, you can see that the limit of my exponential of x is exponential of x. Okay, over here we are going to apply the formula of the product of the function, so I'm going to do it directly because you are two advanced learners, you know how to apply the derivative on a product of two function. So I'm just going to do it inside the bracket. So the derivative of x is 1 into x e power x minus x of e power x. Okay, and the derivative of my 1 is 0 upon derivative of x squared is this, and derivative of x cubed is 3x cubed squared. And here derivative of my x is 1, derivative of my tangent of x is secant square x whole square. Okay, that's it. Now let us apply the limit. Now before applying the limit, let us try to simplify this portion. This and this gets cancelled, and here. Now here you can see, though I haven't applied the limit yet, but I can see that once when I apply the limit, I am going to have a unique answer. So in this portion, I'm no more going to apply my L'Hopital. Okay, so once over here, I'm just applying the limit. So it is giving me secant square of 0 is 1, so 1 upon 1 square is 1, so it is 1. This and this gets. Now I'm just coming to my destiny. Life is getting easier, finally, into 1. So now once when I apply my limit, I am going to have a nice answer, of course. So you see it is 1 upon 2. Finally, I got the answer. So you see, that's how I get rid from the indeterminate form, and I just got a unique limit value. So this is the significance of your L'Hopital rule. Okay, so I hope this entire strategy is clear to you related to the form of 0 by 0. Now inshallah, in the next video we're going to discuss the other indeterminate form. So that's all for today. Inshallah, I'll see you in the next video. Take good care of yourself in this lockdown, and pray for all of us.